So the idea is this, right? You start with something and you get some value out, and we're thinking about, okay, what's the opposite of that? What's the inverse? Right, I want to go from, if I go originally from 2 to 8, how do I go back from 8 to 2? Well, if I cube something, the inverse operation is cube rooting it, right? And to obtain this expression for the inverse relation, what we could do is we could swap them, okay? I said there's also a geometrical interpretation. What I mean by that is that there's something visually that's going on. We started to talk about it, right? Let's just look at an example, right? So y equals to x plus 3. Okay, what I want to do here is, in order to get a better idea of what's happening visually, we want to look at maybe the domain and range of the original and also the inverse that we create, okay? So that's something to keep in mind, the domain and range, right? So let's look at the original curve. Y equals to x plus 3, we know what that's going to look like. That's going to look something like this. So we'll pass through, it's got a gradient of 1. I want to use a ruler here, so it's nice and straight. Just like this. Now, what's the inverse of this expression? Y equals to x plus 3. What's the opposite of that, right? If I'm adding 3 to something, yeah, that's it. That's the inverse, right? The inverse is y equals to x minus 3. What's that going to look like visually? Again, still a straight line. This time the y-intercept is at minus 3, right? So we can graph that as well. The domain and range for these, though, what's the domain and range for both of these? Yeah, they're both the same, aren't they? Nothing too interesting going on there. The domain for this linear function, negative infinity to infinity, and the range as well, negative infinity to infinity. And same thing over here. Right, and that's because linear functions, the domain and range are always for all the values that we can see. Okay, so nothing too interesting going on there. Let's look at a different type of function though. What have we got here? A parabola. Now, so something is a bit strange about a parabola, because what happens when you try and find the inverse of a parabola? Yeah, it does. What do we have to do? What was the algebraic method? We swap the values, right? If I swap the values, I get, I'll do this in another color. If I swap the values, I'll get, yes, x equals to y squared. But not only that, what do we have to do to actually find the function? Yeah, we have to find the relations, we have to make y the subject, right? So we take the square root of both sides, not forgetting that we have to do positive negative cases. That actually creates, well, you can think about them as two functions. And that's why I haven't called them inverse functions just yet, okay? Because sometimes when you take the inverse, you create something that's not necessarily a function, right? Why is that? Well, y equals to x squared, it looks like this. It's our normal parabola, okay? Now, y equals to plus or minus the square root of x, right? If you remember, the square root of x looks like this. But if you put a negative in front of the whole function, do you remember what happens there? What kind of transformation is that? If you put the negative in front of the whole function. Yeah? So anytime you see a positive, right, it becomes a negative, it's actually a reflection in the x-axis there. Yeah? See, all of these things are intertwined.
That's why you put two different ones in the decimal.
Yeah, that's right. Yeah. I had to do two different ones because I couldn't work out how to do necessarily all at the same time. Apparently there is a way to do it. That's another thing. Can you find for me the domain and range of this one? Domain and range. Okay, domain and range for my parabola. Go, Harry.
Oh, the first one?
Yep. The black curve. So the domain is, yep, negative infinity to infinity.
You want me to do the range as well?
Yeah, yes, go the range.
Is it the weird bracket though?
Ah, yeah, good, because we take the value, we include the value.
Yeah, 0 to infinity.
Well done, okay.
Yeah.
And for my blue curve, what's my domain and range, Callum?
Domain would be 0 to infinity. The square bracket.
Good, because we're including that value.
And the range would just be negative infinity.
Okay. Ooh, I've seen an observation. What did you say, Laura? The domain and ranges have swapped. I wonder if that's something that's going to be true for this one as well. Has anyone done this one? It will be. Eva, what kind of graphs are these again?
Hyperbolas?
They are hyperbolas. Okay. And from your assignment, hopefully we're familiar with how these shift. What is this x minus 5 going to do on the denominator?
Five, that way.
Yeah, it's going to change where the vertical asymptote is, right? So at x equals to 5, we're going to have an asymptote. So it looks something like this. And what's the inverse of this? Well, we can swap the x and y values to find it. This becomes a little bit tricky to find because there's all these because there's all these fractions, it's a little bit tricky. We can still do it, right? Multiply both sides by y minus 5. And then, what do I want to make the subject again? Y. What do I do?
Divided by x
Okay,
plus 5.
good. Now, Angus, what does this shift do? If I have a plus 5 on the outside. Good. I have a whole number on the outside. I'm shifting it up. I get 5 up here. That becomes my new horizontal asymptote. My vertical asymptote doesn't really change though. So now it's going to look something like this. Roughly like this maybe. Something like that. This one's a little bit hard to see what's going on. I'll put the domain and range again. Let's just confirm that they have swapped like we saw before. Domain of my original black curve here is going to be from negative infinity to 5. And then what do we have to do after that? We have to do a union. And then 5 to infinity. And same thing for the range. This is just going to be from negative infinity and 0 to infinity. And what about my blue curve? Well, for my blue curve, same idea, right? So the domain is from negative infinity to 0, 0 to infinity. And then the range, now we've shifted up, right? So we're going from negative infinity to negative 5. Sorry, not negative 5, positive 5. And then 5 to infinity. So, have they swapped here? Looks like they have. Yep. So that's something that we can notice. That's actually not the geometrical thing that I'm looking for in particular, though. The geometrical thing I'm talking about is, you guys mentioned it last time that when we were looking at the function and its inverse, you saw something happening with the curves themselves. Do you still see it happening over here? What did we, where's my remote? What did we say we saw last time happening? I remember Laura saying something in particular about how the curves are moving. What was that suggestion?
Rotating.
Yeah, they're rotating. So the suggestion was that, like, if you look at this one over here, it looks like the parabola is kind of rotated this way. Would you say it's the same for this straight line here? Has it rotated somewhat? I did, I'm so happy. Okay, sorry guys, just coming back. Sorry, Matt, can you say what you said again? That was really good. Can you say what you said again? That was really good. So, no, what was the analogy you used, you said? So in primary school, you might have done those paintings, like the butterfly ones, where you kind of like fold them in half, and then you got them on both sides. Do you remember that? Yeah, so this one over here is actually what's happening geometrically, right? Is actually what we are taking our curves, we're not rotating them, and we're not shifting them. I'll tell you why, because you can take one of them and you can say, it looks like this one you're rotating, right? But then you take, for example, this cubic that we looked at, and we realize we're not rotating it, because if you rotated it, the curve would be going a different way, okay? So, I'll give you a clue. We are actually, we are smushing it. That's not the technical mathematical term. Where are we smushing it? Diagonally. What do you mean diagonally?
Diagonally along the origin.
Diagonally, so you take the origin here, and you draw a diagonal line, and you're saying that's like a piece of paper that you're folding? Is that what you're kind of saying? That's exactly what's happening. What is that line, by the way? We're swapping. Actually, not we're swapping. We're reflecting. This is the geometrical application. We're reflecting the curve in the line y equals to x. Now, I think the really cool thing is, sorry, can I rub this stuff off here?
Yeah.
Okay, I'm going to rub this stuff off here because I need a bit more space. The really cool thing is to look at why we're reflecting it in y equals to x. Okay? Because, this is why. Remember how I said algebraically we're swapping the x and y values? Okay? So if you had a point, for example, when x is equal to 4 here, y is equal to 16. Okay? That's one point there, right? So when x is equal to 4, y is equal to 16. 4, 16. What happens when you put 16 in here? When x is equal to 16, yeah, y equals to 4. So 16, 4. I said that we can think about it as the points. But there's a point, actually there's a series of points where when you swap them, nothing actually happens. 0, 0 is one of them. And 0, 0 is one of them. But actually, yes, yeah. Any point along y equals to x, if you swap their x and y coordinates, nothing will happen, right? There's a point here where they intersect, and they both lie on that point. I think it's actually 1, 1. So this is obviously not to scale, right? Okay. So can you see that, right? This is why it reflects in the line y equals to x. Because when you're swapping the x and y values, there's a point where nothing happens, or a series of points, anything along the line y equals to x. Just to see this really clear, I might get you guys to do this in a moment, okay? We can see this happening, right? So let's get a ruler. And by ruler, I mean one of these. Let's take our axis. Yeah, you need it to be, because otherwise it doesn't come through. And you can try this with any shape. Let's just do our parabola, right? We'll do our parabola. And what you need to do is, just to see that this really works, okay, you draw your parabola. Okay. And then we have to find out where y equals to x is. So roughly it's about here, okay? Yeah, so what you want to do to make sure that this actually works, you just want to go over your... Can you guys see that, by the way? Am I blocking it? Yeah. Yeah, anyone who does art's really going to like this activity. So you rub it, just go over it again, so there's a lot more lead on there.
Is that what you're doing?
Yeah, so when we're doing this, right, you know, don't do plotting. When you're trying to find the inverse, don't plot points, don't use decimals, that's cheap. Trying to find but go into your test and bring in a piece of baking paper. And then... I mean, if they let you bring your own paper, who says to say you can't bring baking paper? Right? We fold it along that diagonal line. Well, fingers crossed. And so, I don't know if I folded that correctly. I definitely didn't. Let's try. There we go. So, now how you get the inverse is any place you see the curve, you need to go over. Okay? So you can see the curve here. You can see it over here. And you can also see it around here. If you push hard enough, that should create your inverse function. It's a little bit faint there. Can you see that? So there's your inverse function. Can you see that? How cool is that, right? Now, in the worksheet I'm about to give you, okay, you are asked to do that. If you'd like a piece of baking paper to try that, I'm sure you would, I will give you this worksheet to hand out. Matt's going to hand out those for me, thank you. And if you'd like a piece of baking paper to try this out, Harry will hand those out.